For those of you on YouTube, we covered the linear function, the absolute value function. The power functions, y is equal to x squared and y is equal to x cubed. X squared looks like what?
Parabola.
Parabola. That should be something you remember as well. And why is a parabola always above the x-axis? Because if you square something, it makes it positive. If you cube something, is it always positive? No, which is why a cubic can go below the x-axis. Kind of has that snake-like shape to it. Then we have y is equal to x to the fourth and y is equal to x to the fifth. Do you think x to the fourth looks more like x squared or more like x cubed? X squared, because it's even. It will be a little bit steeper and a little bit more pronounced at the bottom. I'm not asking you to show that difference on the test. If you graphed x squared and x to the fourth, they look the same, that's fine. The point is that you understand that those look similar to each other. Whereas x to the fifth looks a lot more like x to the third. It's a little bit more flattened out at 0 than x to the third is. We have our y equals the square root of x, and y is equal to the cube root of x. Or in other words, this is x to the 1/2 power. This is x to the 1/3 power. That's what that means. The square root function, we talked about square roots in domain, and you can only have the square root of positive numbers, which is why this graph looks like that. But we said you can take the cube root of any number. Therefore, the cube root function has a domain of all real numbers. And so it goes both to the negative and to the positive. If you had y is equal to the fourth root of x, which is x to the 1/4, or y is equal to the fifth root of x, which is x to the 1/5, those will follow kind of like the ones above. Remember when we saw a fourth root function when we were doing domain, you can't take the fourth root of negatives either. So it looks a lot like the square root function. And the fifth root, because it's odd, you can take the fifth root of negatives. So it looks like the cube root function. So again, I'm not going to try to have you show the difference between the two. These basically look the same. These basically look the same. Okay? Other root functions. Y is equal to x to the 2/3 power. Or in other words, cube root of x squared. Now this is interesting as you think about it. I can square any number. I can square positives, I can square negatives. But if you square something, it's going to become positive. And if you take a cube root of a positive, you get another positive. So that tells us it's always going to be above the x-axis. So it kind of has that square root function, but it always stays above the x-axis. I call it the bird function. Kind of looks like a bird. What if we flip them around? Y is equal to x to the 3/2, otherwise known as the square root of x cubed. And watch what happens here. If we plug in a negative value, what is a negative cubed? A negative. Can you take the square root of a negative? No, so you can't have any negatives. Another thing I want you to notice is that 3/2 is the same thing as 1.5, which is between 1 and 2. Remember that an x squared looks like that, whereas x to the first power looks like that. So x to the 3/2 is going to be right in between there. And I'm not asking you to necessarily show that so much, but it just kind of trails off somewhere between a line and a parabola because it's 1/2. And you can't have any negatives. And finally, our last ones are our reciprocal functions. Y is equal to 1 over x, and y is equal to 1 over x squared. Notice that we've already talked about domain of a lot of these type of functions, and you should recognize that what value can you not plug in for x here? 0. So therefore, this graph has what we call a vertical asymptote at 0. An asymptote is a line that the graph approaches but does not touch. Okay? A line that the graph approaches. It also has a horizontal asymptote at 0 as well, because 0 is a number that you cannot obtain from an output. That means that whatever number you plug in for x, you're never going to get out 0 for y. I don't care what you try. There's no number that will give you 0 for y. And then the graph kind of follows those asymptotes. It has that shape. As it gets infinitely closer to that line, how do you think this last one is going to be different than the first one? What happens if you square something? Makes it positive. So how will the graph look different if it makes it positive?
It's going to be, they'll both have to be above.
They'll both be above the x-axis. Exactly. When you understand why something works the way it does, that's when you're doing math. When you're just crunching numbers and doing what you're told to do, that's not doing math. The word math actually comes from the Greek word monthano, and it means I understand. So when you understand why something works, that's the true nature of math. Anybody know what came first, algebra or geometry? Geometry. Geometry was the first mathematics, the true understanding. I'm guessing for most people, that was kind of the math that you didn't appreciate as much, right? Okay, I get it. First was geometry, then trigonometry, then calculus, then algebra, thousands of years later. So algebra is kind of the last of the mathematics. It's one that obviously we spend a lot of time on here, but yeah. So anyway, here we go. We want to do this page. We want to talk about being able to look at a graph and do it very quickly, okay? I'll try to make my point to you. If I had x squared minus 2x minus 8, could you factor that? Could you give me the two numbers that multiply -8 that add a -2? What are they? 4 and negative 4 and 2? You guys can do that quickly, right? That's called a skill because you can do it in less than a second generally. You guys can see that in less than 1 second. Could you imagine if factoring this took you guys a good, 2 to 3 minutes? This would be a tough class to get through, wouldn't it? We have to go from processes to skills. And so we want to take graphing from a process and we will make it a skill to where you can do it quickly. Literally to where you look at a graph and you know within a second what the graph looks like. And that's what we're going to teach you over the course of the next few days. So suppose we have a function g of x. And what we're going to do is we're going to say it's basically the same thing as f of x, but with a constant added on the end. What that's going to do is if you put a constant added on the end of a function, it's going to create a vertical shift. And literally what it will do is it will move it up or down c units. Simple as that. Whereas if we look at a function of this form, g of x changes to f of x minus c, notice that the minus c is here as opposed to the plus c is out there. That's going to shift it horizontally. Left or right c units. Okay? Here's the most important part of the entire unit. I will reference this all the time, and this is the key to understanding all the stuff we're going to do after this as well. Notice how the C is on the outside. If it's on the outside, it impacts it vertically. If it's on the inside, as you see here, it impacts it horizontally. Outside is vertical, inside is horizontal, all the time. Well, we'll get to that probably 2 or 3 more times before we're done with this. Also, I need you to understand that in this situation, the left or right is opposite of what you think. Now, this really did help second or first hour as we talked about this. You don't have to write this down, but just follow with me. Suppose I had x minus 4 quantity squared plus y plus 3 quantity squared is equal to 100. Does anybody remember from the last test that you took what shape that makes if we were to graph it? It does make a circle with a radius of 10. And what was the center of the circle? It was located at 4, negative 3. Notice how it's opposite and opposite. When it's on the inside, it's opposite of what you think. See what I'm saying? So it wasn't left 4, it was right 4. It wasn't up 3, it was down 3. Okay? So when it's on the inside, it's opposite. When it's on the outside, it's exactly what you think. So what we want to be able to do is be able to look at a graph like x squared minus 3 and say, hey, I know that makes the shape of a parabola. That's the parent function. And then what happens from there is we shift it. Is the minus 3 on the outside or the inside? It's on the outside. This would be an example of on the inside. See that? Here's what it would look like on the inside if it was right here. It would be x minus 3 quantity squared. See the difference? That's outside. That's inside. So since it's on the outside, does it impact it vertically or horizontally? Vertically. And it's just going to move it down 3. So we want to be able to look at that graph and say, oh yeah, parabola down 3. Boom. The next one, we see the square root function. We memorize what that looks like. Do you remember what the square root function looks like? Yep, good. Kind of starts here and just trails off. Is the minus 4 on the inside or the outside? Inside. So is it going to impact it horizontally or vertically? Horizontally. Is it going to be right 4 or left 4? Right. Opposite of what you think, so move it right 4. Very good. Next one, I see the cube, so I know it has the shape of a cubic. What are the two transformations I have here?
Down 2 to left 3.
Good, so you see the minus 2, which means that I have a vertical shift down 2. You see the plus 3, which means it's left 3. So I take this, I move it left 3 and down 2. Whoop. That wasn't very good, Mr. Gens. Try the last one on your own. Take a glance up when you think you got it. I see the absolute value makes a V shape, and then I see that it's right 4 and down 3. We good? Questions going once, twice, thrice. Let's move to our last part, which is our vertical reflections. Suppose you had g of x, and that became negative f of x. Notice, is the negative on the outside or inside?
Outside.
It's on the outside. Anything on the outside impacts it vertically. So that's going to be a flip up and down, okay? Suppose I had g of x changes to f of negative x. Is that on the inside or outside?
Inside.
Inside. And so you can see again, if it's on the inside, it impacts it in a horizontal manner. So that's also going to be a flip, but instead of up and down, it's going to be a flip of left to right. I draw those because every once in a while I have students that they can't remember the difference between vertical and horizontal. So So we'll do these four, we'll be done for the day. Identify the parent function and then graph the new function with the transformation. So each of these has a negative involved in it in some way. I think that your last one is different on your paper, is that correct? You could just change it to what I have, negative quantity x plus 5, sorry about that. And so the square root function I know looks like this. The negative is on the outside. See if you can draw what it would look like if the negative is on the outside. Take your best guess. What would it look like if you have the negative on the outside? And your answer should look like that. A flip vertically. We good? Okay. I think that this is the most important example to consider when we're talking about these type of flips. Because I'm going to do another one. Suppose it was square root of negative x. That would then flip it. That's what it would look like that. And furthermore, if I had negative root of negative x, that would flip it both vertically and horizontally, and it would look like that. So you could produce all four by placing the negatives in different spots. Okay, next one. We see the negative in front of the x. That causes a problem. Here's the best way to deal with the negative in front of the x is to factor it out. And here's what it looks like to factor it out. I don't actually factor it out of the parentheses, but I factor it like this. I'm going to factor a negative from the negative x to make it positive x. I'm going to factor a negative from the positive 3 to make it a negative 3, and it's that quantity squared. And so the way that we carry out this is we know it makes the shape of a parabola, but we start on the inside and we work our way out. So we start here. This is what kind of a shift?
Right 3.
Right 3. And then after we shift it right 3, we then take it and we flip it horizontally. So I'm first going to take and shift it right 3, like so. And then when we say we flip it horizontally, that doesn't mean it flips over the y-axis. We just flip it from where it is. If we flip it from where it is it the same?
Yeah.
Absolutely. And that should make sense if you actually look at this. If we were to square the negative, we get a positive. And so that matches with that graph. They're actually the exact same graphs. The next one I'm going to take, and I'm also going to factor out that negative to make the x positive and the 1 negative. I have 3 transformations going on here. Let's work from the inside out. What's the first transformation? Right 1. So I'm going to draw that in this light shape or light shade here. Right 1, that's the first transformation. What's the second transformation?
Flip it.
Flip it. Is this a flip horizontally or vertically?
Horizontal.
This is a horizontal flip, so it's going to flip like that. Everybody see that? It'll flip like this. So this part's going to flip over here. So I'm going to get rid of this. I'm going to draw it like, there we go. So I flipped it horizontally, and then what's the last transformation? Then I have to move it up 4. So I'm going to get rid of that. I'm going to take it, and I'm going to move it up 4 units. And so as you notice here, it is shifted to the right 1. It's shifted up 4 units, and it's flipped horizontally. Try the last one on your own.
just did it up, not down.
I see the x plus 5 on the inside, that tells me it's a shift to the left 5 units. I see the negative on the outside, that means it's a vertical flip, so it's upside down. There we have it. Good? Okay. I'm pretty good about just telling you guys, work at your own pace and get done before the test, but this is pretty important that we soak this in right now. So go ahead, take out your assignments. And I want you to turn to this page right here, because it's not a lot, okay? This assignment right here that says parent functions and transformations, and it should say easier. This is the easier part. For example, the first one is just a line that shifted down 3 units. We should be able to see that pretty quick and sketch it right away. A lot of these graphs should go hopefully fairly quickly for you. I mean, each one probably, 10 to 20 seconds, you could sketch it down. These are the ones we want to happen quickly. On Monday and Tuesday, we start to look at ones that are going to take you a little bit longer. The instruction is pretty short on Monday, you're going to have a lot of time, but it will go a lot better if you have this sheet here done. So I don't care where you are in your homework, I would encourage you, get this sheet done this weekend, okay? As I post the answer key, or the answer key is posted, the hard copy I have up here, I also list off to the left and the right the domain and range. You don't have to list the domain and the range. That was something I had students do years ago as we needed that practice. You guys can just sketch the graph and that's it. And we want them to be, these are not problems where you want to spend 3 minutes per problem. It should hopefully happen pretty quickly for you.
This one too.
Nope, just the front and the back of that sheet that says easier at the end.
Oh, okay,
And then the next one, these are a little bit harder.
okay.
Okay?
Yeah, that one.